Okay, we've made it to Module 3, and Module 3, the title is Elements of Chemistry, and a lot of what Module 3, Chapter 17, has to do with can be kind of described with this right here. What is in here? Okay, so got a cup full of ice. Now, can we describe, say, an ice cube? Sure. It's got certain physical properties, and that's one thing you'll be talking about in this chapter is physical properties versus chemical properties, as well as physical change versus chemical change. So what would happen if I just left this cup of ice sitting out on my desk? Well, what would happen? Of course, you know it's going to melt, right? It's going to turn into water. But at a atomic level or a molecular level, is there really a change there? Isn't it still water? Couldn't I, if I let it melt and it forms a pool of water, couldn't I pour this back into an ice cube tray and put it in the right conditions, put it back in the freezer? Wouldn't I wind up with solid water again, also known as ice? Sure, right? So keep that in mind when you start to read about physical properties, physical changes, as well as phases of matter. Because just in that, we would be talking about two different phases of water. When it's in its solid form, we call it ice. When it's in its liquid form, we call it, of course, water. And even when it's in its gas form, it's still water. We just call it water vapor. And think about the different physical properties of those different types. It could be the same stuff. It's still water. It's still H2O. But it'll have different physical properties. This has different physical properties than liquid water does. And certainly it has different physical properties than gaseous water does. So a substance can have varying physical properties depending upon its phase. So, gosh, that's half the chapter. If you understood what I just said, you've understood half the chapter, really. Keep phases in mind, keep physical and chemical properties in mind, and keep physical and chemical changes in mind as you read the material. Okay, it's time to try the Chapter 17 Explore activity. You've been trying this at home, haven't you? You want to learn about chemistry, don't you? Well, here's what you need. You need a cup. You need some baking soda. Now, first of all, can you describe the properties of baking soda? Physical properties of baking soda. It's a powder. It's white. Let's put a little bit of baking soda in here. And we're going to add some vinegar. And what are the physical properties of vinegar? Well, it's a liquid. It's clear. Now are either of these flammable? Probably not, right? We can try to light either one of them, but they're probably not flammable. Now let's combine the vinegar and the baking soda. See that? Foamy, foamy. Add a little more vinegar here. All right. Now you've probably done that before. No big surprises. But check this out. What happens if I strike a match? What's going to happen when I drop the match into the cup? Oh, well, let's try that again. Golly. Well, what is going on? What is going on here? It's like there's some other substance that has been created that is causing my match to get snuffed out every time I put it into the cup. There must be a chemical reaction, a chemical change occurring. For those of you who took Physical Science 1, remember Physical Science 1 was for the most part just physics with a lot of the math stripped out. And a lot of times you'll hear people define physics as the study of the interactions between matter and energy, or sometimes matter and energy are actually kind of a false dichotomy. They're kind of two sides of the same coin. Well, chemistry is defined as the study of matter and the transformations it can undergo. For example, here's a beautiful diamond ring. Of course, we know that diamond is really just carbon that was subjected to the proper pressure and temperature, and so that's a transformation. That's a transformation that carbon has undergone to create that substance we call a diamond. Now notice, here's a picture of a moon landing, right? There's a reason why certain materials are used to make up that spacecraft. There are certain properties that certain materials have that make them useful in a spacecraft. So that's really another core purpose of chemistry, is that chemistry is a materials science. And without chemistry, a lot of our modern world would not be possible. So chemistry really does inform various branches of science. Sometimes it's called the central science, because really none of the others can exist without atoms, and really atoms are one of the main focuses of chemistry. So it's a materials science. Again, we wouldn't have all these wonderful materials, these products that make our modern life so easy, if it weren't for chemistry. So for example, there's all kinds of examples when we look at just a kitchen, and this is detailed in your textbook, but we got the windows in this little cabinet here that are made of glass. It's a processed silicon dioxide. Of course, we have safe drinking water thanks to chemistry, and we even have fluoridation in a lot of our drinking water, which helps us to prevent cavities. Of course, every morning you wake up, we have a caffeinated solution that helps to get us get our eyes open in the morning. Here's a polymer that's created this nice countertop inside the refrigerator. Of course, you've got medicines and all kinds of food preservatives that help extend the shelf life of foods. We've got a metal alloy here that we use for cooking. Of course, we wouldn't have lights if it weren't for the knowledge we have of the internal workings of atoms. Either we're producing energy, either using coal that we've burned, or we're using perhaps a nuclear power plant that creates the energy, and we know how to harness it. Fertilizers that help to grow our produce larger, more quickly, less disease, less risk of spoilage. This is all chemistry, which is really quite fascinating. So that's why chemistry is called the central science. It's part of our daily lives, and it's part of our laws as well. This is more than 70% of all legislation placed before Congress addresses science-related questions and issues. And that's why, even if you don't wind up being a scientist for a career, it is important for you to be a scientifically literate citizen. So take a look at this statement. Collagen cross-link inhibitors that significantly reverse various aspects of aging have recently been discovered. So what do you think? Should they? Well, what do you think of any of these? Did you understand the question to begin with, or the terminology to begin with? If you don't understand it, there's no way you can make a decision on it. And so that's why it's so very important to stay informed, to be a scientifically literate member of society, because there are so many issues that hinge on sound science, and it's important for the electorate to be able to understand these topics in order to vote for the proper legislators who will be properly informed to pass good policy on these topics. One thing that makes chemistry a bit of an abstract science is the fact that its central object, the focus of study, is an atom. And atoms are really, really small, as we've talked about. The fact that we can't even see atoms. And in fact, even with the best visible microscopes, we can't see them because atoms are smaller than visible wavelengths of light. So when you can't see what you're studying, it gets a little more abstract. But to give you a feel for how small atoms are, notice this slide says that a single grain of sand contains 125 million trillion atoms. So can we just put that number into perspective here? So here's 125 million. But remember, we're talking about 125 million trillion. So we got to start adding zeros. There's your billions, and here's millions, and here's thousands, And finally, down to below the 1,000 level, hundreds and tens. That's 125 million trillion atoms. Essentially what we're talking about is very, very small objects. In fact, you can have, here's a nice sand dune. And your book has a picture of this. 250,000 dunes this size. If you're able to imagine that many dunes, sand dunes, and think about all the grains of sand that make up those sand dunes, that would be equivalent to 125 million trillion grains of sand. So atoms are indeed small. Another way of thinking about it is imagine an apple. And to think about the number of atoms that are in an apple, one way of thinking about that is to think about how many apples would fit into the entire Earth. If you could hollow out the Earth and start filling it with apples, the number of apples required to fill up the Earth is the same, or essentially the same, as the number of atoms that make up one single apple. Okay, so here's the question. Are atoms made of molecules, or are molecules made of atoms? I'm not going to answer this one, but if you don't know, go back to chapter 15, review that material, because you'll find the answer there. One clue is this particular screen here. Notice we got a water molecule, and well, that's it. You got a water molecule, and what is it made of? It's made of 2 hydrogen atoms and an oxygen atom. So that should give you a little information about the previous slide. Now, the next part of the chapter gets into physical properties versus chemical properties. And we talked about this a little bit when we dealt with the example of the cup of ice and water in general. The different phases of water have different physical properties. For example, liquid water is visible. You can see it. Water vapor, not talking about steam, because steam is actually just condensed water vapor. It's tiny little water droplets, liquid water droplets. But true water vapor is invisible. Human eye cannot see it. So the physical properties of the same material, water, can be different depending on the phase. The physical property has to do with the look or the feel of a substance. That should not be confused with chemical properties. Chemical properties have to do with how substances perhaps transform into other substances. For example, iron. Iron has a chemical property that it can turn into iron oxide, rust, in the presence of air and water. So now that you understand what a physical property is, notice that we have to draw a distinction between physical and chemical changes. A physical change is where you have a change in the physical properties of a substance. For example, melting ice. One is a solid, one is a liquid. So therefore, they've got different shapes. But typically one thing you can tell a physical change is that it is reversible. If you take that liquid water, gather it up again, put it in cold conditions, it will become solid ice again. So quite often, physical changes are ones that are reversible. A chemical change quite often is not reversible. For example, they give the example of baking soda. When it reacts with vinegar to form carbon dioxide, you can't just take the carbon dioxide and somehow get baking soda and vinegar back out of it. That is an irreversible process. So that is typically when a new substance is formed. For example, even the iron example. When iron combines with water in the presence of air, it creates iron oxide. You don't reverse that. You're left with a new substance. So during a chemical change, a new substance is formed as the atoms rearrange themselves. So quite often in a physical change, the atoms really don't change. They might change how they might be bonded together with other atoms or molecules, but there are no new substances created. In a chemical change, that is the case. So for example, combustion is a chemical change. Why is that? You got methane, which is also known as natural gas. When combusted in the presence of oxygen, of course you need to have oxygen for combustion to occur, the atoms rearrange themselves and you wind up with a new substance. Two new substances, in fact. You start out with oxygen and methane, you wind up with water and carbon dioxide. That is a chemical change. So again, to reinforce, a physical change occurs when you've imposed a new set of conditions on a material. So for example, the ice cube. You put it in a warm room and it is going to melt. And there's going to be physical changes that occur. In a chemical change, but in a physical change, like the ice cube to water example, it's still H2O. It's still a water molecule. It's just the water molecules have greater distance between themselves. They're not quite as bound to each other as the water molecules are when they're in a crystalline structure we call the solid ice. However, in a chemical change, you have a new material that is formed. Now, both of them result in changes in physical appearance. So when a truck rusts and you go from iron to rust, iron to iron oxide, the iron has different physical properties than the iron oxide. Likewise, ice cube has different physical properties than liquid water. So they both have changes in physical appearance. However, the one is reversible and the other is not, and that's a good way of telling the difference between a physical and chemical change. So if you're confident that you understand the difference between physical and chemical changes, now's a good time to test yourself. Go to the skills test and take a swing at the physical and chemical changes skills test, and notice that there is again, a tutorial video that goes along with it to help you work your way through the interface. Okay, part of learning any science, in this case chemistry, is learning the jargon. And so in section 17.7, it makes the distinction between elements and atoms. And really the key to understanding the difference between elements and atoms is that atoms make up elements. So, and it's a one-way street in the sense that elements are made of atoms, but not the other way around. So atoms make up elements. Elements do not make up atoms. And so the examples given here are like gold. Gold, a hunk of gold, what they call the macroscopic scale, something you can actually see or somehow sense. That amount of gold is actually made up of a lot of tiny, tiny little gold atoms. So it's the atoms that make up the elemental form. So the atoms of gold make up the macroscopic elemental form of gold. So an element is used when we're referring to relatively large quantities of something. But it turns out that a hunk of gold or a small ingot of gold or a huge, huge boulder of gold is made up of individual gold atoms. The difference between each of those different examples, the big boulder versus the small little ingot, is just the number of gold atoms that make up that elemental gold. However, take for example oxygen. Take a good deep breath in, and what you're breathing in is what's called elemental oxygen. That's how it's found in nature. And it turns out that oxygen is not just found as just one single oxygen atom. There's actually two oxygen atoms combined to form O2. And so the oxygen that we breathe, what we call elemental oxygen, is actually two oxygen atoms combined. So the elemental or macroscopic form of oxygen is what we call elemental oxygen is actually O2. And that O2 is made up of two oxygen atoms. Looks like a bunch of eyes. All right, but that's essentially the distinction between elements and atoms. Now we're going to move on to what are called compounds. Compounds are substances that consist of different elements. So for example, they give the example of sodium chloride, okay, which is a sodium atom and a chlorine atom. Or here's ammonia, right? It's got a nitrogen atom and 3 hydrogen atoms. Those are compounds. Compounds consist of different elements, and they have properties uniquely different from the elements from which they are made. And that example is given at the bottom of page 377, where sodium chloride, NaCl. Sodium itself is a highly reactive metal, and chlorine is a poisonous gas. You wouldn't want to deal with either of these substances in their elemental form, but you combine them together and make a compound, and it's delicious on popcorn. So now that you know what a compound is, we can use, and actually now that you know what elements are, we can start talking about chemical formulas, like for example, that example of O2, what we breathe. This is just a way of representing the two oxygen atoms. We call it O2. Instead of having to draw two oxygen atoms linked up, we just write O2. Or rather than drawing a bunch of atoms and say, okay, a sodium atom is linked up with a chlorine atom, we just write it out as NaCl. That stands for table salt. So ammonia, NH3, again, rather than drawing it out, we say, okay, a nitrogen atom combines with 3 hydrogen atoms and forms ammonia. So this is what's called the chemical formula. These are the common names for some of the very, very common substances we deal with in everyday life. And this is just the last section of chapter 17, 17.8. Essentially, it talks about how to name compounds. So, for example, our good old sodium chloride, what we do is NaCl, we start from the left, we name it out, and we quite often use an IDE at the end. So sodium, chlorine, when we put them together, sodium chloride. And then if there are little subscripts, quite often you'll add a little prefix. So when there's a 1, which is usually just not even written, it's just understood, it's mono. When it's 2 is di, 3 is tri, 4 is tetra. So for example, here's carbon and oxygen. So we say carbon, and normally you would say oxide, right? But we understand there's actually a 1 down here, and that gives us carbon monoxide. And then we do the same thing because carbon and oxygen can get together in a couple of different ways. So it's not good enough to just say carbon oxide because there's possibly several different forms. So we have carbon and oxygen again, but now it's a carbon linking up with 2 oxygens, and that winds up being carbon dioxide. Okay, we're getting down to the end of chapter 17. Good time to work on your second skills test of the module. This one involves, well, you can watch a video with good old Daniel Radcliffe rattling off the elements of the periodic table, which is a lot of fun. But again, watch the video to get a feel for what the interface is all about. Another thing you can tackle at this point is a lab activity. Again, it's going to teach you more about periodic table trends, some of the trends that you find in the periodic table. There's no need to memorize the periodic table, but it is useful to learn some of the trends contained within the periodic table. And of course, once you've done all that, to make sure that you've understood everything, go through the readiness assurance test. And here are your answers for the chapter 17 readiness assurance test.